Hello, everyone. Thank you for joining us for today's webinar, Mastering NPDES Ammonia Regulations, Field Insights and Game-Changing Technology. I'm Heather Masaccio, your host from Water Online and Life Science Connect. Our speaker today is Adam Jennings, Wastewater Applications Development Manager with Hach. Just a bit of housekeeping first. If you have a question for our speaker or wish to share any thoughts of your own, please submit it through the Q&A box on your screen. If you run into any problems with the stream today, please try refreshing your browser first. If your problem persists, use the Q&A tool to submit a question and I'll help get you back on track. We do have a few poll questions on your screen and would appreciate your feedback and thoughts. This event will be available on demand, normally within about 24 hours. Just use the same link you used today. All right, with all that said, I'm going to hand it over to Adam to begin the presentation.
Yeah, thanks, Heather. Appreciate the time. Thanks for joining today. Like Heather said, we're going to be talking about ammonia monitoring and some permit information, and we'll just get into it. So we'll go into some NH3, NH4 monitoring. We'll kind of talk about what the differences are between ammonia and ammonium. We use those terms pretty interchangeably in the field often, but there are some really important nuances between what those two terms mean and what they are. We'll get into ammonia treatment. We'll cover some nitrification challenges, talk about some of the different technologies that we use in the field for measuring NH3 and NH4 online. And then we'll get into a new solution that we have available at Hach to help folks in the field better understand and monitor and control processes for ammonia removal. Then we'll get some Q&A at the end. So you'll have some time to ask some questions if you have any. So why do we measure NH3 and NH4? Well, maybe it's obvious, maybe it's not. So the main reason that we measure and monitor for ammonia is that it causes water body impairment. So nitrogen in the environment causes multiple different issues. Some things ranging from environmental toxicity to eutrophication, and potentially some issues where we're converting ammonia into nitrate, and that is causing issues with our drinking water systems with nitrate intrusion and that sort of thing. So when we're talking about monitoring NH3 and NH4 for these situations where we have possible water body impairment, we have NPDES permits that are being distributed throughout our country at wastewater treatment plants, and it's a regulated parameter. So we have lots of treatment plants that have NPDES permit regulations for ammonia or another form of nitrogen that may include ammonia. So we have 4,200 permits in the U.S. as of a few years ago. That have nutrient regulations, whether that's phosphorus or nitrogen forms, species. And then an additional 5,700-ish, some of those have been converted into actual permit regulations at this point. So I think this 4,200 is probably on the low side. And these are all just designed to help our facilities match and meet good environmental regulation for the wastewater that's coming out of them, so that we're not causing these problems, environmental toxicity, eutrophication, and things like that. So, some other reasons and some things that we want to dive into a little bit on why we want to measure NH3 and NH4 is that, like I said, it's on our permits. So the thing that drives most of our treatment plants to monitor for any parameter is it's a permit regulated parameter or something to do with safety at the treatment plant, that sort of thing. And in this case, we've talked about ammonia as one of the most commonly permitted values at a treatment plant, and that includes ammonia's inside of some of these other forms of nitrogen. And so, we typically measure our parameters that we are required to in the lab, and those are taken off of composite samples or grab samples, and there's different ways that we're required to monitor those. And there's many treatment plants moving into online measurement. So the traditional permitting for treatment plants. You got BOD, you've got TSS, some form of bacteria, that sort of thing. Those are on all permits, pH, things like that. But as we move into nutrients and we're having to measure and treat biologically things like phosphorus and nitrogen species, things get a little bit more complicated, and it gets a little more important for us to be seeing what's happening throughout a 24-hour period and then seasonally and things like that. So in addition to our standard regulation monitoring that we have to do, a lot of facilities are moving into stages where they're like, okay, we're treating, we're doing things well, our ammonia removal is what it should be, or we're moving into a new regulation where we feel like we're going to need some more data, some more information, some more visibility into our process. And that's where these online sensors can help us optimize and really just find the balance between compliance risk and efficiency. Because there's a balance there. We can't spend too much money, but we need to try to find the balance where we have enough online, enough data to be able to properly run our process. Some of those permits, what do they look like? This is just a snip of a permit and some of the regulations that someone might have. So, like on this particular facility, you're seeing things like seasonal limits, where in the summer months the values might be a little bit tighter. They're required to remove more, or in the winter months, or vice versa, depending on the permit. So we have seasonal changes in these limits. They can be very significant, milligrams per liter different from one season to the next. Most facilities are required to do 24-hour composite sampling for maybe daily maximums, weekly averages, monthly averages, things like that. One of the things we're seeing a lot more of in the last 10 years is we used to be pretty concentration based from a regulatory standpoint. And that's moving a little bit, and we're getting a lot of permits now where it's not just concentration anymore, it's also pounds based. That's been happening for quite a few years, but it's getting to be pretty much a standard in the nutrient space, where pounds based limits are really common. And the real challenge there is we're I travel around the country and I see a lot of wastewater plants and talk to a lot of folks, and a lot of cities across the country are growing rapidly. And so that's where the pinch happens, because if we're getting pounds based limits based on a current flow rate, and then our city or our municipality flow is increasing by substantial amounts during that period, then we start pushing those pounds based limits maybe sooner than we expected, versus just a concentration base. And I threw wet testing on here, so that may be a familiar term. Maybe you have wet testing requirements. They're usually a few times a year, 2-3 times a year. And one of the interesting things about that is if you have higher levels of ammonia and higher levels of pH, you could end up having failures with your bioassay or your wet testing because of ammonia concentration. So that could be a whole nother webinar in itself, but it's an interesting thing to think about. If you're constantly failing wet testing, you might take a look at your pH in your system near the effluent and your ammonia concentration at that time. So what's ammonia, and what is ammonium? It's a pH dependent process. And so what we have here is you have ammonia is the gaseous form, and this is the form that really causes toxicity to aquatic life. I mentioned wet testing. If you're required to use Cerodaphnia, for example, there's a certain toxicity level that happens where the reproduction rate doesn't you don't meet the reproduction rate or the mortality rate. And that can happen if there's too much of this toxic form, if the pH is too far into the basic side of things, so at or above 8 pH. Most municipalities are around 7, and so it's a little bit less of an issue, because around 7 pH, our wastewater plants are seeing primarily or exclusively the ionic form, so ammonium. And so this is a big deal. Sometimes systems inside of our treatment process can increase or decrease pH, and there's various ways that happens. But when we're monitoring inside the plant, we usually we're so close to that 7 pH that it's just in the ionic form, but we need to keep an eye on our pH. So that also plays a role in when we're doing and we're talking about measurement technologies, and I'll get into that a little bit here later. So this graphic is just covering some of the common permit regulated values we end up with on permits. So total nitrogen or TN, total inorganic nitrogen, TIN, total Kjeldahl nitrogen, TKN. And the reason why I threw it up like this, there's other things I could put in this chart, but I sort of simplified it to just show that the commonality between all of these different forms. Sometimes we have just ammonia on the permit, but ammonia is a piece or a part, and it plays a big role in all of these different forms of nitrogen that we're getting permit regulations on. And so it makes it so that ammonia is the most commonly found nutrient on permits. And so if you don't have it already, it may be coming in the future. So when we're talking about treating for ammonia, it's a biological process, and there are lots of things, and I probably didn't even list everything that could cause issues with our biological process. We have certain organisms that treat for ammonia, and when we're doing biological ammonia removal, we're converting ammonia ultimately through a few different forms to nitrogen gas. We're going from ammonia to nitrate, and then if we're denitrifying, we're trying to remove that nitrate and convert it to nitrogen gas. So normally I'd have a slide that kind of goes over that, but I kind of wanted to focus a little bit more on some of these other things that play a big role in how efficient, how well we are doing from a permit concentration and removal perspective. And so these are some of the drivers, and we'll get into these individually. So kicking it off, not in any specific order of importance, because they're all very important, but I started off with temperature. This is a common situation that we run into. We are sitting right now in what I would call a shoulder season. So we're coming out of the cold winter months when, as you can see here, in the winter months, our nitrification rates. So when we're trying to convert ammonia to nitrate and nitrite, those rates can be half of what they are in the summer in some cases. And so what we do typically is we have to change our solids, our wasting concentration, and that sort of thing to help deal with some of these effects on temperature. You can see how the nitrification rate changes from different temperatures. The warmer it gets, the better we get at it, and maybe the less organisms that we need in our system to treat for ammonia. So big pressure, temperature is a big deal. So it's hard sometimes when we're transitioning from one season to the next to hit the temperatures just right because of how the seasons are so dynamic, and you get false springs and things like that. You're like, summer's here, and then never mind, winter's back. It can be a challenging thing, which like I'm mentioning, SRT. So SRT is just a common way that we sort of quantify the solids that we have in our system. And when we say solids, that's just a combination of inert matter in the system, and then also our organisms. These bugs that are doing the work that we need them to do to treat for nitrogen forms, whether it's ammonia or nitrate, nitrite, and that sort of thing. And the temperature and the solids concentration all come together in this mixture that we need to maintain to keep nitrification rates at the levels that we need in all the seasons. So it's a dynamic process that we have to constantly monitor and maintain proper solids concentrations that equate to the right amount of bugs to treat nitrogen, ammonia specifically, to the levels that we need to. So I put this one in here because we have more and more regulations. Even if you had an ammonia regulation, whether it's straight ammonia or total nitrogen, or another form that includes ammonia, for a long time, and some of these facilities were getting tighter regulations, and those values, when they're up around higher levels, the cost to treat and remove ammonia, it's one of the most expensive things that we do at a wastewater plant, because nitrification is just an expensive process. We have large horsepower blowers that are pushing air into water, and depending on how your processes run and how low your permit is, determines pretty closely how much energy we're going to have to spend to remove it. You can see here as we get down into these values, which we're hitting some very low values, whether it's just ammonia or total nitrogen, total inorganic nitrogen, the cost to treat gets quite a bit more expensive, and so it makes it that much more important for us to spend a lot of time making sure that we're as optimized as we can be for the amount of ammonia that we need to remove. And so that's an important piece to look at. Alkalinity. Sometimes this is overlooked. It may seem like commonplace information and knowledge, but when we go into treatment plants and we're looking at facilities that are struggling or struggling in certain seasons, maybe not even all the time, sometimes the issue turns out to be a limited alkalinity availability. So the nitrification rate in our system, how well we remove ammonia biologically, is directly related to how much alkalinity we have available. And so if there's not enough in certain seasons, certain times of the year, certain loading conditions, if we have more ammonia coming in, the alkalinity available for these organisms to do the work that they need to do can be limited, causing some issues and maybe some bleed through in our aeration systems. So very important, especially when when we have designs going on and we're trying to figure out how big the basins need to be, what's the SRT that we're going to need to have, the solids concentration. All of that should be brought into the equation, making sure that we're always checking the nitrification rates, and if we have data throughout the year, because that can change how much alkalinity we have available throughout the year and throughout process changes that we have. So on that same note, if we're talking about a total nitrogen situation, so the conversation's largely around ammonia, but you can't have a conversation strictly about ammonia without talking about nitrification and denitrification in some plants. So there are a lot of facilities out there that have internal recycles. So we have the ability to take some of the flow from the end of an aerobic zone and bring it back around to an anoxic zone, maybe in the front half of the plant. And we take that nitrate rich, because when we're converting ammonia to nitrite and nitrate in an aerated system, your ammonia is going down, your nitrate is going up, and you can take that nitrate-rich liquor back around to a denitrification zone, a zone that doesn't have any air, oxygen-free environment, and you have some carbon present. You can remove the nitrate, and that removal of nitrate can help reduce the organic load then going through your aerobic zone. So you don't have to remove those same organics oxically when you have, say, a total nitrogen limit or a total inorganic nitrogen limit. And the other bonus to that is if we are doing that process and we're bringing that nitrate-rich liquor back around and we're doing some denitrification, we're gaining a little bit of alkalinity. So we're putting a few credit points onto our aerobic system to help maybe increase or have better or more stable nitrification. To win in both ways, we do it that way. So loading conditions. This is a super dynamic situation, and it looks different for every plant. This is one plant's data. The blue line represents just diurnal loading, ammonia loading over a couple week period. And you can see, you have a pattern. This is not a surprise that we would see high loading at certain times of the day, low loading at other times of the day. And that dynamic change in load happens maybe differently in certain seasons and depending on your processes. So internal side streams, they can be sneaky. Sometimes our side streams, when we're doing solids removal, when we're doing anaerobic digestion, aerobic digestion, and we're dewatering on site, some of that cleaner water that's coming back to the plant can have high loads of ammonia. So all these things play a role in the dynamic load condition that we have at a treatment plant. But what do we usually do? Matt, maybe I should back up. We don't usually do it today, but we have in the past been really traditional about how we do dissolved oxygen, providing dissolved oxygen to our organisms. And you can see that black line. This is like a real common way that we've done this traditionally, and lots of facilities still run this way, where the dissolved oxygen is controlled and based on a solid set point. So we're just trying to maintain a solid set point. And the challenge there is it's sort of a surrogate measurement, right? We're trying to remove ammonia in this case, but we're measuring DO. Well, there's a little bit of squish in there, so we don't always know. Even though we have a good solid DO, we're keeping that DO nice and stable all the way across the board. As we saw from the previous slide, the loading is so dynamic and it changes quite a bit. And so are there some gains that we can make by changing the way that we control our dissolved oxygen? And so that brings us to an ammonia-based idea. So when we talk about ammonia-based aeration control, sometimes it sounds like a really complicated thing, and maybe something that's unfamiliar for those who aren't doing it, that is. And so what it shows here is a modeled view of what could it look like and compared to the straight baseline DO control. And so you can see where this blue line is tracking with what we saw on the loading conditions coming into the treatment plant, rather than just a straight line across, and the overall values of DO needed to actually treat in those conditions that sometimes is so low you almost don't even have enough air for mixing, which is a consideration as well if you go to ammonia-based aeration. But the idea here is we're treating and we're measuring, we're using the control point is a direct read. So if we use an ammonia sensor, an ammonia analyzer, to do a feedback control loop as part of this DO control, we can end up being much more tight in our control, save some energy, and use air when it's needed and not use air when it's not, because like I mentioned, it's one of the most, if not the most expensive process we do in wastewater treatment in a lot of cases. So just pitch in ammonia-based aeration as a direct control rather than using DO as a surrogate control. So talked about ammonia and the need for monitoring. So how do we do that online? And here are some common technologies that we use in our field. And so titration it's a very old and common way to do measurement for a lot of different parameters. And we are able to do this online. It's the problem with the titration is in most cases, this technology for online measurement, real-time online measurement, is a little more cost prohibitive. Photometric, really common. Photometric is a form of, we're making color in the water, and we're measuring this with some optical sensors and understanding the concentration of the hue of the color to help us correlate that directly to an ammonia measurement. Some challenges with that is you have more frequent reagent changes. Optical fouling is pretty common, and temperature and color can be an issue at times. Changing temperatures and color in the sample can affect the value that you're getting. Then we have ion selective electrodes. They're usually a lower investment cost. There are cases where as we get lower with our ammonia concentration, we're running at low levels, below 1 or even lower, significantly lower. The calibration, the maintenance at those low concentrations can be quite a bit higher. Then we have gas sensing electrode, and this is where we're going to camp a little bit today, because this is the technology that we've improved on and added some nice features to help us monitor in real time and take out some of these common challenges that we come across with other measurement technologies. We're going to have less drifting issues because this sensor and the setup that we have has more calibration, automatic calibration, auto cleaning. The gas sensing electrode is very accurate at low levels. And so this is a real key, because when we're doing ammonia-based aeration and we have low limits, a lot of times we're at very low levels, and we need to have good accuracy to make sure we're maintaining proper dissolved oxygen in the system, regardless of how you're controlling that. It's an important measurement. And it's unaffected by temperature and color changes, which is a really nice benefit. So that brings us to the new technology that we have that will help us and hopefully be a nice tool for everyone in the field to be able to maybe move towards ammonia-based aeration, or just get a much tighter view and less maintenance on ammonia monitoring in aeration basins out in the weather, or in effluent conditions and other places in your treatment plant. And so what this looks like is it's not a new technology for us. We've been using the gas sensing electrode for quite a few years. We've got a legacy of these analyzers and how they've moved from one technology form to the next, and how we deliver this gas sensing electrode technology, and that lands us on the new NH6000. And so what this is it's a situation where we've taken the gas sensing electrode, we keep the same technology because it's been a really great technology for low-level nutrient removal, when we're trying to do total inorganic nitrogen removal, ammonia, total Kaldol nitrogen removal, as ammonia is a part of all of those things. We can do that now with 50% less maintenance than we had with our previous versions. These are values that are based on some of our technology in the past, the predecessor, the Amtex. And we're using 30% less reagents. One of the huge improvements that we've made to this setup is a 70% lighter filter. And we're going to talk about that a little bit more. We've added some new aggressive air cleaning to our new filtration system, which enables a much longer time period in between manual cleaning. So, if you've had to deal with filters in the past for any reason, cleaning filters is probably one of the least enjoyable things about maintaining online analyzers. And so it's a nice improvement to have to do less of that with this new technology. So when we're talking about the gas sensing electrode technology, I mentioned some of the benefits. And one of the things that we find is really helpful is the GSE to make the measurement only needs sodium hydroxide as a reagent. And so, some of the colorimetric methods require more than that to make that colorimetric analysis, but it's a pretty simple technology, the GSE. And so all we're doing, and this is why ammonia, the form of ammonia versus ammonium, matters, because like I talked about, in municipal systems with a pH around 7, you have a very high concentration, if not all, of your ammonium presents itself as the ionic form. And so what we're doing with the sodium hydroxide is we're increasing the pH to a high enough level that it converts all of the ionic form to the gaseous form. And then we have a permeable membrane in this gas sensing electrode that then reads the gaseous form. And so that's a really slick way to do it. We make sure we get a complete picture of the forms of ammonia and ammonium. And the sodium hydroxide is a less toxic way to do it versus a colorimetric sample. And like I mentioned before, color is not an issue here. So with online analyzers, when we're talking about wet chemistry analyzers, the sticking point, like I mentioned before, is filtration can be frustrating. Filtration is hard to handle in some cases, and cleaning it is not usually something that everybody likes to do. So we tried to simplify this and make it as easy as possible by changing the way that we do our filtration. So we've dropped the weight significantly. Our old system, the Filtrax, if you're familiar, used to weigh about 16 pounds, a little over 16 pounds. Now we're down to about 7. I've seen these in the field where, it would be a miracle if someone could pull one of these. You have to be a pretty stout person to pull one out with one hand. But this new filter is much easier for that. You can do that, and I've seen people pull it out with one hand. Sometimes installation height with the old filter is a little bit of an issue. So we've shrunk it down so you can fit this into lower flow areas. the way that you change the filter panel has been significantly improved. This one just uses a snap in and snap out with a button. So you just press it in, it snaps into place. When you need to remove it, you press a button on the side and it pops right out. So there's no tubes or anything that you have to mess with. It's a quick and easy, simple way to pop the filter out, do any manual cleaning you need to do, and then put it back in. And like I mentioned, the new filter boasts some really significantly increased and aggressive air bubble cleaning. So you can see in the picture, it's kind of small, but this is one of our filters when it's doing an air bubble scour, and it's clearly visible even within an aeration basin. So this makes it so that the manual cleaning that we've had to do on filters in the past is significantly less. That's a big bonus, I think. And the last part is, when we have flow conditions that are pressing on a filter, one of the things that we've done to help with those issues is a 30-degree pivot. So this filter panel that's in the water, the flow is pushing on it, it can move side to side to 30 degrees and help relieve some of that pressure on the filter itself. So how do we get reliable results? So we're trying to nitrify, we're trying to remove ammonia for whichever permit or multiple permit regulations we have. And like I mentioned, a lot of it starts with the filtration. We've already talked about, we've got a good technology. We've been using that technology for many, many years. It's a trusted technology, the GSE. But filtration is one of the key points that make sure that we have a good sample going to the analyzer and the maintenance has been reduced and it's just an easier way to clean and that sort of thing. Automatic calibration, super helpful. This system the NH6000 automatically calibrates at regular frequencies to help keep this sensor running exactly as accurate as it can be without having drifting issues. So, some of the ion selective electrodes over time, they start getting foul, they start drifting. That's not going to be the case with this. You're not going to see that drift that you would with an ion selective electrode. So that's a nice benefit. We have a new automatic cleaning system that cleans the entire wetted chemistry portions of the analyzer all the way down to the filter. It doesn't clean the filter with any chemicals, but it will clean that line all the way to the filter, which is a really impressive improvement that our team has come up with to help make sure you guys have good samples, valid, accurate data that's comparable to the lab. And this is one of the greatest things. They've come up with a new automatic grab sample feature. So I don't know if you're anything like what I've experienced in the past. I've been operating plants and we're trying to figure out, why is my analyzer not matching the lab? My values are off. I'm not sure what's going on. And that happens very often. And so one of my recommendations when we're taking grab samples out in the field is, you want to make sure your sample is representative. You want to get in really close to wherever this analyzer is pulling a sample or where the sensor is. You want to take that, say if it's in mixed liquor, you don't want to wait to filter those samples. You want to field filter those samples right away and make sure that there's no more biological activity happening, on the long drive back to the lab, or when we take a sample and if we don't filter it, some folks will put it on a counter, wait for it to settle, then take a sample. And all of those things introduce error. And those things can also produce a situation where your lab sample isn't matching your grab sample. And so what we have here is an automatic grab sample feature where we have a 100 ml sample container inside the analyzer. And it's pulling a filtered sample through the filter. The analyzer is splitting the sample, taking a reading, and then giving you the rest of that sample to then take the exact same sample back to the lab, run it in the lab, and then you've taken out all of the sampling questions. Did I get it close enough to the sample point? Did I wait too long? Did I not filter it quickly enough? And many other things that can go wrong in the sampling and analysis procedures. It helps remove all those questions so that we can be confident that our online analyzer is matching the lab appropriately. There are a number of self-diagnostics this has, and all of these things play together to help stop the drift. So some results from the field. I always like seeing data, and we have multiple ranges of this analyzer: high range, low range, medium range, and the R values came back fantastic. These are all samples that were taken with the automatic grab sample feature, so that you know that you took the sample, that it's the same sample that's being analyzed from the analyzer as you're taking to the field, which really helps square up this R value. So a field example, we installed one of these analyzers at a customer site, and the city of Grapevine decided that they wanted to start making process changes because of the new data that they have from this online analyzer. And so what you're looking at here is a few weeks of data. The bars that you're seeing is the ammonia levels in their aeration basin as it came from the analyzer in their lab testing. And the little dots are the blower amps. So they had two blowers. They have multiple trains in their system. So they put this analyzer on one of their trains and then started doing some testing on basically a third of their facility. And they found that the online data was coming back consistent and good and matching their lab. And so they started making changes to their process to see, is it possible that they could save some energy costs? And so they started lowering the amperage on some of their blowers in a manual action. And you can see all the way, they brought their amps from 375 amps combined to a point on the 23rd where they were able to turn off a whole blower and still maintain values that were under their permit limit at that time of the year, which was 6 milligrams per liter. And so the takeaway here is online analytics gives us the ability to even try to optimize our system by reducing aeration at certain times or altogether. And in this case, they saved about 18% when you annualize that. That came out to around $74,000 a year if they were to run in this manner throughout the year. There's carbon savings available, so a lot of wins here by having the visibility of online ammonia monitoring with this new NH6000. So just finishing up on total nitrogen, I talked a little bit about it before, but we've focused quite a bit on ammonia. So I want to just take a minute and talk about nitrate. So when we have limits, total nitrogen, total inorganic nitrogen, those include nitrite and nitrate. And so at a facility, if you want to measure and get a good sense for what total nitrogen is in your facility or in your aeration basins, if you were to measure nitrate and nitrite, or nitrate only and ammonia, you're going to get a really good sense for the majority of how your process is treating for total nitrogen and total inorganic nitrogen. So there's a couple of ways we measure nitrate. Photometrically, we'll do this similarly to ammonia. Different color, but we're still trying to produce a color and then read that color. And in the same way, we have some challenges with optical fouling on photometric analysis. You also have that here with nitrate measurements. You can also do it with ion selective electrodes. So nitrate can be measured with an ion selective electrode. Same situation where if we're running at very low levels, like say we want to measure nitrate in a swing zone, or we want to measure it in a denitrification zone, those levels can get pretty low and that can increase maintenance. And in this case, with a nitrate measurement that we have available, there is a reagent-free direct read way to do that. And some of the benefits here is you have an automatic cleaning system, and you have high low-level accuracy with less maintenance in most cases. And so with the NT3100, this sensor reads NOx optically, so NOx, so nitrite plus nitrate. And this will help you, it doesn't speciate those two, but it will give you a great idea of the nitrate and nitrite present combined in a NOx measurement, where you can use that combined with the ammonia, ammonia analyzer NH6000, and get a really good picture of what your total nitrogen is and your total inorganic nitrogen. One of the big strengths of this is it has it's turbidity compensated, and we've updated from its predecessor from a few years ago the user maintenance, changing out the wiper blade. You no longer have that little cap that some people get frustrated with because it's so small and we drop it between the grading. That's all been taken out of the equation. Changing out wipers are so much easier, and you can see here some of the data below. This is over I think it's like 2 weeks of data, and we've got some dots in there. Those are grab sample correlative data points. So you can see the accuracy has been really good. This is in a mixed liquor setting. So I just didn't want to leave it without throwing it together with the complete picture of total inorganic nitrogen monitoring or total nitrogen monitoring, where we're making sure we understand what's happening with both of those parameters in real time. Effluent in an aeration basin are both. It's all a great way to help understand our process and troubleshoot. So final thoughts. One of the things that I think would be super helpful, and this is just something I've been thinking about quite a bit, and we're seeing a few folks do this, when we have big projects coming up, we're getting a new ammonia limit, we're getting a new total nitrogen limit. We should consider thinking about getting more data for our engineering firms to help us design our systems as best as they can, because a lot of times we go into a design situation and we're taking grab samples and doing lots of composite sampling over a period of time, but it may be just in a few weeks or maybe twice a year if we get lots of data. But understanding what's happening diurnally, day and night, where we're struggling, and finding out the time of day when side streams are coming in because they're sneaky and they bring high loads of nutrients, ammonia, phosphorus, and other things into our system, and sometimes we don't realize how impactful that is. So having some online sensors to understand when and how our treatment processes are doing, with all of this visibility and data, we can take that and hand it to our engineering firms and come up with a nice plan, maybe a more accurate plan of when we have issues and how big we need to make our basins, and alkalinity concerns and things like that. So my thought process is consider adding online sensors before projects get going to get some great data that can help drive the design of our new facilities. Another note on the GSE technology, it's very fast. We get some really good data at proper time frames so that we can make good informed decisions, and our aeration systems can be controlled off of that data, and it's quick enough so that we can capture the changes. Again, DO is a surrogate measurement, and consider looking at ammonia-based aeration. Either way, we're using an online sensor to control our system, and so it makes a lot of sense to me to take out some of that squishiness that we have with DO and start leaning a little bit more on ammonia as the direct read to help control our systems. You can use these ammonia monitoring systems in post-aeration systems, post-aeration banks, effluent, and when you start seeing some issues in these separate systems, you can go in and go back into the process with grab sampling and figure out where some of these problems are happening. It's a really nice way to start getting into problems before they become a real issue for us. And then consider nitrate monitoring, as those who might have total nitrogen limits coming, or increased total nitrogen, total inorganic nitrogen, NH6000 plus NT3100 equals a ton of visibility. So really helpful. Make changes with confidence and know whether you're helping the process or causing problems when you make these changes. And that wraps it up for today. So thanks so much for taking time and listening to this chat. Hopefully you find some nuggets of useful information.
Thank you so much, Adam. I'm going to pop back on. Thank you for the great information, and thank you to all who've been going along with us and submitting your questions. We're going to go ahead and get to our Q&A portion of the webinar right now. And let's see here. I will begin with the first one. Okay, Adam, the question is, how do evolving regulations impact ammonia monitoring requirements, and how can facilities stay ahead of changes?
Well, it's funny that you asked that, because we are just in the last few slides, when we have increased ammonia limits. When I say increase, I mean tighter regulation. Tighter regulation means that the margin of error gets so much smaller in our facilities. And so if we're relying on 24-hour composite sampling for our NPDES permit to really hone in on when problems are happening or stay ahead of problems before they happen, it makes it really difficult. So these online monitoring solutions like the NH6000, the NT3100 are really key to helping us manage those tighter margins that we have to operate in when we get tighter regulation for these parameters.
Okay, very good. Thank you so much. And back to the audience questions. And this question is asking, what are the most common compliance challenges facilities face with ammonia monitoring, and how does the NH6000 SC help address them?
Yeah, well, so some of that was covered in this talk. One of the challenges is nitrification can change really fast. If we have an issue with getting enough air to our organisms in an oxic zone that are doing nitrification, that can present itself in a real hurry. And if we have online analyzers like the NH6000 monitoring the end of a basin for a change in that ammonia concentration and have alarm set points in place for those, we can diagnose those problems before they become a composite sample issue later. So, like I mentioned, most of the time we're doing a composite sample for our permit requirements for NPDES, but we don't know when the problem happened necessarily. We can see, oh yeah, the concentration in the composite sampler is higher, but what happened? How did it happen? When did it happen? So having the visibility 24 hours a day, 365, is super helpful in diagnosing when those problems are happening.
Thank you so much, Adam. Now we have a question from Taylor. Taylor's asking, I have had abnormally high ammonia in my effluent, but my MLSS, SRT, and everything else looks great. The only thing that has changed in my effluent is the chlorine concentration has been slightly elevated. Does this affect ammonia?
So ammonia reacts with chlorine. I'm not sure exactly what could be causing a higher ammonia limit or ammonia bleed through in your plant. We'd have to look at some more data. There's lots of causes. We talked about quite a few of those dynamic pressures that can cause a higher level of ammonia. But if you're seeing a higher chlorine demand in your system, you might be having higher nitrite values. But I think to really answer and dig into your question, we have to get a little bit more data behind it to help you out. But I don't know if you have contact with your seller in your area, but they'd be happy to connect you to everybody on our team.
Okay, very good. Thank you so much, Adam. And the next question is asking, can you please verify if the online measurements for ammonia is for process control only and not for compliance monitoring purposes? Thank you.
Yeah, really great question. In the U.S., we don't have any online ammonia monitoring technologies that are approved for regulatory reporting, to my knowledge. It's not impossible. There could be someone out there, because many states are now they have what's called primacy, and so many states are running their own NPDES permit compliance, and so the reality is that there are lab approved methodologies that, even though we're using a similar technology like ISE, for example, so an ion selective electrode in the lab could be certified for regulatory reporting, but an ion selective measurement in a probe in the field is not typically approved. And so it's usually the methodology. And even though we're using the same technology as a lot of approved methods, for ammonia specifically, the gas sensing electrode, to my knowledge, is not an approved method for regulatory reporting. And so, if the concern is ever, well, my regulator might regulate me on this because it's at my compliance point. Well, the reality is that it's not a regulated methodology. So the methodology itself has to be approved by your regulator.
Very good. Thank you so much, Adam. Now, this next question is asking, in the case graph showing diurnal fluctuations of the influent ammonia, at some point the treated water showed higher concentrations of ammonia while the influent was not changing. Why did this happen?
That's a great question. And I don't know the exact answer. So I wouldn't be able to tell you exactly what happened in that situation. But like we talked about, there are multiple dynamic pressures on how well or how poorly the facility treats for ammonia. And so even though you might have had a similar concentration of ammonia coming into the plant, there could have been changes inside the plant that could cause problems. Sometimes we toxify, I guess, maybe would be a word, our own treatment facilities by what we do internally with our side streams. And there are certain cases where those side streams can bring back high concentrations of things that can cause, high amounts of polymer, even in some cases, can cause nitrification inhibition inside the plant. So even though the loading may be very similar, the plant's ability, the organism's ability to be able to treat that ammonia could get inhibited by some sort of a toxic load, for example, even from the influent.
Very good. Thank you, Adam. The next audience member would like to know how often the online sensor takes samples.
Great question. So it's an adjustable time frame. So the fastest values you can get back are every 5 minutes. And that's usually plenty fast enough to do things like ammonia-based aeration. But if you don't need values quite that fast, you can change the sample time frame to a higher value, 10 minutes or more. But 5 minutes is as fast as is the fastest you can get a value.
Okay, excellent. Thank you very much. Moving on, another audience member would like to know, are ammonia polishing technologies a viable option for achieving stringent ammonia limits in the effluent? Can you help with that?
Sure. Yeah, we can go into that a little bit, but yeah, when you have high levels of ammonia in a side stream, for example, coming from a centrate, maybe a centrate treatment or belt filter press, that sort of thing. If you can remove some of that ammonia in a side stream deammonification basin, so that you're not having to treat that in the mainstream, that's absolutely a viable option.
Very good. Thank you so much. And moving on, let's see, this question is asking, what effect have you seen from low pH on nitrification? Let's say 6.7-ish. That's from Michelle.
Yeah, well, great question. Yeah, so pH is an interesting measurement point, and we do it all the time in lots of different places, whether we're doing grab samples in a wastewater facility or we're measuring online with a online pH probe. But and it's a really inexpensive way to kind of get a pulse on a surrogate measurement again. So what pH is it's very similar to DO when we're talking about alkalinity. So pH is a surrogate measurement that doesn't really give us a direct read on what the alkalinity concentration is in the aeration basin or at an effluent. And so you can use pH, and that can give you maybe an indicator. But the problem is, by the time your pH value starts dropping, you could already be having nitrification issues because the building blocks of each SU of pH are built on a whole stack of alkalinity points. So by the time the pH changes, you may already be in a situation. So it's sort of a lagging indicator. So measuring alkalinity is a far more efficient and better way to do that when you can, to understand whether we're having nitrification or could have really soon some nitrification issues. Great question.
Great. Thank you so much, Adam. Our next question. Does Hach plan to get this technology to be approved for Method Update Rule 40 CFR Part 136?
That is a very specific regulation question that I do not know the answer to. Well, I should say this. I know part of the answer. I don't know that regulation specifically, but we are not seeking regulatory approval for the NH6000 methodology at this time.
Okay, thanks, Adam. And how about this question? How frequently does this model analyze and transmit the data of the wastewater?
Well, it's pretty similar to, I think, one of the other questions. It's about 5 minutes. You can get a sample value back every 5 minutes, and that can be transmitted directly to your SCADA system every 5 minutes.
Very good. And now I see this on this next question coming in. This question is asking, let's see, reducing the number of sensors for tie-in with, is it SCADA? System is common observation. How do you safeguard against bad data being fed to the SCADA?
So if I'm understanding the question, let's say you have 4 aeration trains, and you're thinking maybe if you have one ammonia sensor in one basin, and then you're mirroring the control of the next basin from that one sensor, and you're saying, how do we make sure that we ensure good data to control both basins off of one sensor? If I'm following the question right, I'm not sure. You want to make sure you have all the checks and balances in place to make sure that that one sensor is properly understanding what it's reading. But to the point of the question, if we've made sure that the analyzer is reading correctly by using automatic calibration, automatic self-cleaning for the filter and the analyzer itself. And so it's doing checkpoints and calibrating itself regularly. And we know the analyzer in that basin is good. The question might be, well, how do we know that the treatment in the basin that it's mirroring by, we've maybe tried to reduce the amount of sensors we have, is accurate? And that is a great question, because there are cases, and I've seen it multiple times, where there are changes in that specific basin that don't necessarily correlate directly with the basin that you're controlling from. So there's a potential risk there with not having actual direct read sensors in each of those basins.
Very good. I think we have time for one more question. This question is asking the City of Grapevine testing graph, why the amps came back up in the end of September. Can you explain that?
Repeat that one more time. I didn't quite catch it.
Absolutely. So the question is asking about the City of Grapevine testing graph. Why did the amps come back up at the end of September?
Yeah, good question. So they were just doing a quick trial to see what could be possible. So it was just a testing period. So they dropped the amperage on those blowers, 2 of them together, until they got low enough, and then they realized we can keep going, we can keep dropping the amperage. And so they brought the blower amps back up on one of them, and then completely turned off the other around that middle September or end of September timeframe. And they ran that way for a while, realized they can do it that way, and then decided to start bringing it back up, because we were ending the trial period in just a few weeks after that. So it was just a test period for them to see how well they could do it.
Okay, very good. Well, thank you so much. And that is our time for today. I want to thank Adam Jennings for sharing his time and his information with all of us. And thank you, the audience, for all these great questions and for watching. If we did not get to your question, no worries. They will be forwarded on to Adam post-event. Remember, this will be available after the webinar has finished. You'll receive a link via email in about 24 hours. Thanks for watching. Have a great day. Bye-bye.